Well, folks, here I have the sum of the first n squares, okay? And this is going to be sort of like a sequel, I guess, to the sum of the first n natural numbers video, which you should definitely check out. I'll link it in the description, and I'll have a card for it right now. So, what is the sum of the first n squares? Well, this is in sigma notation, so we can obviously express this instead as 1 squared plus 2 squared plus 3 squared, on and on, 4 squared, 5 squared, all the way up to however we want to n squared. All right, that's essentially what this notation here, the sigma notation, is saying. And so I'm going to give you 3 ways to prove this, all right? First, we're going to take a little visual approach. So let me take my little diagram out here. And the first thing we're going to do is consider, why are they called squares? Or if they are called squares, why don't we visualize them as squares? And that's exactly what we're going to do. So here's our diagram right here. I'm just going to select that and move it over here to our main area. So here we go. As you can see, we can embed within this the first n squares. So for example, if we have a side length 1 here and 1 here, then this area here is 1 squared. If we have the side length 2 over here and the side length 2 of this square over here as well, then the area of this is going to be 2 squared. All right, I'm going to highlight those and color code them for you guys. And then if we have 3 squared, all right, 3 squared, well, this is a side length of 3 right here, this entire side length. And so that means that the area of this entire square here is also going to be 3 squared. All right, and that also means that this is going to be 4 squared, etc. And I'm just going to have you guys imagine that this goes on up until n arbitrarily in both directions. So this is our square of side length n, all right, which means that the area of this square is going to be n squared, all right, which is right here. And I'm just going to, you know what, just for fun, we're going to add the 4 in here, right, because the area here is going to be 4 squared. All right, so just imagine that this goes on indefinitely until we get to n in both directions like this, which I hope you guys don't have too much trouble imagining. So if we see this, we can see what is the total area of the whole rectangle formed in part by the sum of the first n squares. Well, this largest square is going to be side length n, so we have n and n over here. All right, so this entire rectangle, the entire area here, is going to be what? Well, it's going to be the length times the width, right? And so we have the length as n, and the width, as you can see, is 1 plus 2 plus 3 plus 4 all the way to n, which is going to be the sum of the first n natural numbers. All right, sum as I goes from 1 to n of I, which, if you can tell from the previous video of the sum of the first n natural numbers in 3 ways, that's equal to n plus 1 choose 2. All right, n plus 1 choose 2, which is the same thing as saying n squared plus n over 2, or n times quantity n plus 1. So that's going to be equal to n times n plus 1 choose 2. All right, that's what we have here. All right, that's the total area. Now we want to subtract off the things that we don't want, namely this entire bunch of stuff over here. All right, and so what is all that stuff? Well, let's think about it. First, we have a square of area 1 over here. All right, then we have a square of area 1 over here added to a square of area 2, because this is a side length 1 and this is a side length 2. All right, so I'm going to just draw those in. We have a 1 here, we have a 1 here, here's an area 2. All right, that means that we have the same stuff here, 1 and 2 in these squares above. But what is this? Well, that's going to be, again, here the side length is 1, and here the side length is 3. So we have an area of 3. And you can see where this is going. Essentially, we're going to be incrementing these by the plus 1. So here, this little rectangle here is an area of 4. We have the 3 here, the 2 and the 1. And again, this goes all the way up to n minus 1 in this case, because the nth square is covered by this case over here with the biggest n square. So what is this? Well, each of these little, I guess, slivers or layers represents the sum of the first n natural numbers. And since we're adding them all together, we're summing together the sum of the first n natural numbers. So let me just express that in a way that's more clear. I'm going to call this entire weird sort of pyramid-ish area A, the area that we don't want. All right, and so A is going to be what? We just said it's the sum of the sums of the first n natural numbers. Oh, actually n minus 1 again, because again, the nth is covered by the big square. All right, so that's going to be represented instead as the sum, all right, as k goes from 1 to n minus 1 of the sum as I goes from 1 to k of I, all right, which we know again is n plus 1 choose 2, or in this case k plus 1 choose 2. So we can take this and rewrite it as the sum, all right, as k goes from 1 to n minus 1 of k plus 1 choose 2, like this, all right? And now it's good time to bring in a combinatorial identity, all right? So we're going to pull up this identity right over here. All right, I'm just going to move it back to our main area so that we have a better view of it. All it's saying is that the sum of I choose k as I goes from 1 to n, all right, is equal to n plus 1 choose k plus 1. And so we can apply this, and again, the proof of this, we have a general case where k is equal to 1 in the sum of the first n natural numbers 3 ways video. Once again, check that out if you'd like to see the proof of the of a smaller case of this. All right, and so we can apply that to this over here. And what we get is, again, adjusting for our bounds, we're going to get n plus 1 choose 3. All right, and I encourage you to pause the video and check for yourself. All right, so that's the area of this mess that we don't want here. And now, if we want to find the sum of the first n squares, we simply take the total area, that is the rectangle, and subtract from it this a. All right, and we said the total area is n by n plus 1 choose 2. All right, so n times n plus 1 choose 2. Subtracted from, or we subtract from that, n plus 1 choose 3. All right, and let's see if this in fact gives us a nicer form of the sum of the first n squares. All right, so sum as I goes from 1 to n of I squared. All right, and so what do we get? So n plus 1 choose 2, of course, is going to be n times n plus 1 over 2, and we multiply an n over here. All right, and subtract from that n plus 1 by definition of the combination, n plus 1 times n minus 1 all over 6. All right, and so that we can kind of have a common denominator, we can multiply by 3 on top and bottom like this. So you have 3n times n plus 1. And now we can factor out an n by n plus 1 over 6. All right, and that leaves us with, well, here we have a 3n, and here we subtract from that a minus quantity n minus 1, which becomes minus n plus 1. All right, and this leaves us with n times n plus 1 times 2n plus 1, right, all over 6. And there you have it, folks. That is the sum of the first n squares with a visual proof. I really like this proof personally, so I'm going to put this down as the answer. So you have n times n plus 1 times 2n plus 1 over 6. Great. Now, maybe you have a friend who comes along and says, well, I don't really like shapes, all right? I don't like visual arguments. Maybe they're blind. Who knows? So you want to find a better way to explain it to them. So instead, what we're going to do is we're going to use what's called the Bernoulli method, all right? That's our second method here. So, Bernoulli method. And what this is it skips a few steps from the visual argument, where instead we jump up and start right off with this combinatorial identity right here. This is the key player in the Bernoulli method, all right? I'm going to move that down here again. So, instead what we're going to do using this identity is show, we'll use the identity to stay 2 choose 2, all right, plus 3 choose 2, plus 4 choose 2, all the way up until n choose 2, all right, is equal to n plus 1 choose 3. All right? And so, again, if you want to see the general proof of this with the case where k is equal to 1, please check out the sum of the naturals 3 ways. All right, so we can now expand each of these combinations by definition into, the first one becomes, let's see, 2 times 1 over 2, plus the next one becomes 3 times 2 over 2, plus 4 times 3 over 2 like this, all the way up until n times n minus 1 over 2, all right, those kind of look like h's, but I think you understand what I'm trying to say, is equal to, all right, n plus 1 times n minus 1 all over 6, all right? And now what we can do is multiply by 2 on all sides, because we can get rid of the 2's over here, so these all go away, and this 6 here becomes a 3. Great. So now we have 2 times 1 plus 3 times 2 plus 4 times 3, all the way to n times n minus 1, is equal to n plus 1 by n minus 1 over 3. Now we can express this left-hand side in sigma notation, okay? We can express it as a sum as I goes from 1 to n minus 1 of I times, right, I plus 1, like this. All right, and I encourage you to verify that this is true. And the other side is just going to be the same, n plus 1 by n minus 1 all over 3. But now, look, we want to start with the sum as I goes from 1 to n, right, as we have over here. And so what we're going to do is we're going to actually add a term to both sides to make this upper index the proper n. So what do? We set I equal to n, right? We add to both sides n times n plus 1. All right, if we do that, if we multiply and add n to n plus 1 on both sides, then the left-hand side becomes the sum as I goes from 1 to n of I by I plus 1. All right, and the right-hand side remains the same, n plus 1 by n minus 1 over 3. Subtract from that the n by n plus 1. Great. And now look what happens. If we can expand the sigma over here, and we get I goes from 1 to n of I squared plus I, then look, we have the I squared that we want within it. All right? And again, the right-hand side remains the same right now. So I'm going to leave that as the same thing. I'm going to just put an arrow down to say that they're the same. All right. But now, because the sum is a linear operator, which basically just means that the sum of this sum is equal to the sum separately, as like the sum of I goes from 1 to n of I squared plus the sum as I goes from 1 to n of I. All right? Which means that we have the sum as I goes from 1 to n of I squared, all right, plus the sum as I goes from 1 to n of I, which we of course know once again to be n plus 1 choose 2, which I'm going to write as n by n plus 1 over 2. All right, that's going to be equal to, again, that same expression, all right, below or above. And now, since we want to isolate for the sum of I squared, right, what we can do is sum of I squared as I goes from 1 to n is equal to this right-hand side subtract from that n by n plus 1 over 2. Well, we have an n by n plus 1 over here. So if we have 1 of something minus a half of something, we're left with a half of that something. So we're left with n plus 1 times n minus 1, all right? And forgive me again for the terrible-looking n's that we're drawing here. There we go. It's a bit better. Over 3, all right? And we add to that now n by n plus 1 over 2. And if you notice right away, this is the same thing as saying, all right, the same thing as saying n plus 1 times n minus 1 over 3. This already looks very similar to what we have in the case of the chooses in the first example, okay? So that's something to consider, all right? So again, now let's just find the common denominator, which we have 2 of these, all right, n plus 1 by n minus 1 over 6, and then we add that to 3 by n plus 1. All right, and of course we can factor out an n by n plus 1 over 6, and we get instead here, so we have 2n minus 2 by distributing the 2 into the n minus 1, and we just add to that 3. And ladies and gentlemen, look once again, we have n by n plus 1 by 2n plus 1 all over 6. And there you go. So once again, the sum is n by n plus 1 by 2n plus 1 over 6. So for your friend that is afraid of squares or afraid of visual arguments or is unable to visualize a visual argument due to anything, this is a far more accessible solution. So there you go. But let's say that your friend does not like to see this many chooses, all right? They don't like to see combinations. Maybe they're afraid of combinations and they say, we don't like this. Maybe combinatorics scarred them in 11th grade. So I have a little bit of a better method for you, a bit more advanced method. This involves discrete calculus, all right? Discrete calculus. Let's write that down. And what discrete calculus is it's continuous calculus, traditional calculus without limits, all right? So that seems like everybody's dream. And what we have here is that functions like f of x, all right, they turn into sequences, all right, a of n, or a sub n, all right, the nth entry of a, all right? The derivative then, which looks like dx, becomes what's called the forward difference, all right? And if you would like to see more about the forward difference and discrete calculus, check out, again, my sum of the Fibonacci numbers from 1 to n. That's also going to be carded right now, all right? That has a lot on this too. So that's a delta. So what is that, all right? So we define the forward difference operator. I'm going to write that out, forward difference. So forward difference, all right? We define it as such. So we have delta A at n. So the forward difference of a sequence A at the nth step is equal to A sub n plus 1. So that sequence A evaluated at the next step minus the current step. All right, an. That's it. That is what the derivative is in a discrete form. All right, and you can see the similarities where the derivative of y with respect to x is like the limit as delta x goes to 0 of delta y over delta x. All right, and in this case, you can see the delta actually is very similar. we're just taking the next step size, which in this case in derivatives is a size h, and we're subtracting that from the current step. So you can see the similarities there. All right, a couple more things to notice. All right, the fundamental theorem of discrete calculus. All right, I'm going to write that out. Fundamental theorem of discrete calculus is very similar to the continuous calculus fundamental theorem. All right, the fundamental theorem of discrete calc. And it says this: the sum, all right, as n goes from a to b, of the delta of some sequence u is equal to the original sequence u evaluated from a to b plus 1. All right, the proof for this is actually very quick and easy. And again, take a look at the Fibonacci number sum video on my channel for the proof of this. All right, it eventually involves something called a telescoping sum. All right, and of course, it's very similar if you look at it to the continuous case, where you have the integral from a to b of d of f of x, all right, with respect to df of x. That's equal to f of x evaluated from a to b. All right, so you can see the very similar structures here. So that's the fundamental theorem of discrete calculus. And now, of course, this might seem really random, but I'm going to introduce one more topic before we get to the actual discrete calculus-based proof of the sum of the first n squares. All right, let's introduce what's called falling powers. All right, falling powers. Here they are. So falling powers are defined as such: n to the falling k is defined to be n times n minus 1 times n minus 2, all the way down to n minus k plus 1. All right, you may have seen this before if you've taken combinatorics, where this is essentially when you have integer entries, positive integer entries, it's the permutations, it's the npk essentially, the n permutations, how to permute k objects from n. All right, so that's the npk, which is also equal to n choose k times k factorial. All right, and this is actually also equal to n factorial over quantity n minus k factorial. All right, it goes by many names, but we're going to use this structure here because that's what we want to do. And what's interesting about falling powers is that just like the power rule for traditional derivatives, all right, I'm going to write that out, d dx of x to the k equals kx to the k minus 1 for polynomials, right? Interestingly, the forward difference in discrete calculus, the delta, works the same way as the power rule when you have falling powers. So delta of n to the k is equal to k n to the k minus 1 falling. All right, and using what I've just introduced in this video so far, you should be able to prove this, and I encourage you to pause the video and do it yourself. All right, now let's get to the actual problem. All right, the sum as I goes from 1 to n of I squared. We want to reimagine this as the delta of some function. And so what is I squared? And I'm going to break down I squared into something that's more reminiscent of falling powers. So let's say we can write this as I times I minus 1, very sneakily, and then just add an I back, because this distributes into I squared minus I plus I becomes I squared. And look at this. By definition, you have that this is equal to, this part is equal to I to the falling 2, and by definition, this part is equal to I to the falling 1. And so we can just show that I squared is equal to I to the falling 2 plus I to the falling 1. So let's do that. And this is way more friendly for us because we know that we can apply the power rule in reverse when we take the delta for the fundamental theorem of discrete calculus. All right, so we have I going from 1 to n of I to the falling 2 plus I to the falling 1. All right, and by the fundamental theorem of discrete calculus, we can model this as such. We can take the kind of indefinite integral of the falling powers as the delta in reverse, the delta inverse, if you will. And that's going to be essentially this. It's going to be delta of, well, if I to the falling 2's delta would be 2I to the falling 1, then its inverse delta would be I to the falling 3 over 3, right? So 1/3 I to the falling 3 plus, in this case here, we have 1/2 I to the falling 2, like this. All right, so this is the sum. So sum of I squared can be reimagined as the sum of the delta of this expression here. All right, and what we do from here is we just use the fundamental theorem of discrete calculus, which tells us that the answer to the sum is simply this inside expression here, which I'm going to reproduce real quickly below. All right, here we have it, like this. Evaluated now from the lower bound 1 to the upper bound plus 1, so n plus 1. All right, and so what is this? So first we have 1/3, and then n plus 1 to the falling 3 is going to be n plus 1 times n minus 1. All right? Add that to 1/2 n plus 1 to the following 2 is 1/2 n plus 1 times n, right? And subtract from that, we have 1/3 1 to the following 3 minus 1/2 1 to the following 2. All right? But if you think about it, using the definition of the following powers, right, whenever the base is less than the actual falling power, it's going to go to 0, because at some point when you get that n minus k plus 1, in between the n, which is equal to 1 in our case, when multiplied by n minus 1, that's going to be 0. So everything goes to 0. And so that's going to go to 0, and this goes to 0 like this. And so what you're going to see is this expression here, all right, which we've seen with the Bernoulli method. And so essentially what we get is by taking out the common factor of n by n plus 1, and then not rationalizing, but finding the common denominator by multiplying by 2 here and 3 here, what we get is, well, we have 2n minus 2 by distributing the 2 over here, all right? And we add to that the 3, which is on its own over here, over 6. And of course we get n by n plus 1 by 2n plus 1 over 6. And there you go. That's another way to show that the sum of the first n squares is going to be n by n plus 1 by 2n plus 1 over 6. So I really hope you enjoyed this video. And once again, there's always more than one way to prove a certain problem. And it's just really nice to get many different perspectives, all right? Especially if your friends are afraid of squares or afraid of combinations. And maybe if they're afraid of deltas but not squares, you can show them the visual method, and so on and so forth. Please let me know if you'd like to see 3 more ways to sum the first n squares, or if you'd like to see any other videos of this kind. Thanks so much for watching, and come back next time. Till then.